going to be difficult if you haven't even looked at the practice questions and so on, but at least you'll be able to look at the recording later, and you'll have some perspective and some background. So what we talked about was saturated hydrocarbons. We started with that. So these are, all the carbons are singly bonded. Each carbon is in the center of a tetrahedron, which is a three-dimensional shape. Basically, there are three atoms at the base of the triangle. Carbon is in the center of this pyramid shape called a tetrahedron, and then there's one atom above it. So three atoms below, carbon in the center, one atom above, and this is recurring throughout the entire molecule. And then we simplify by drawing it this way. And I'm just going to give you a little background. Generally speaking, you will not draw the molecules like this on the real exam. You wouldn't draw it like that. Let me just get another piece of paper. Generally speaking, on the real exam, by the way, you're going to get some A4 paper. So you'll see a molecule like this, which is 1, 2, every corner of a geometric figure is a carbon. So 1, 2, 3, and then every end of the line is a carbon if there's nothing else there. So this is a carbon here and a carbon here because there's nothing else there. If there was an OH there, then there's an OH there, but that's not the case. So that must be a carbon. So we have 1, 2, 3, 4, 5 carbons. So on the exam, you would draw it like you would be given a pen from the test center that works, and then you would draw it like this. You would draw it like that. You wouldn't draw it skeletal. You will understand this after you do a bunch of practice questions. Then you're going to start to notice that drawing it this way allows you to be able to envision the three-dimensional shapes when there are questions on stereochemistry. When you draw it this way, it's more difficult to understand the potential stereochemistry. So just, this is a background information. You'll care about this later. So anyway, so we said that these are 5 carbons, and 5 is pent, like the pentagon. So it's this one was going to be a pentane because it's an alkane. It ends in ane. And then this ends in ene, so it's an alkene. You count the carbons, and there's 1, 2, 3, 4, 5, 6 carbons. So we said this has to be a hexene, and we have to identify where the double bond is, and the double bond is attached to the 1, 2 second carbon. So we said this is 2-hexene, or the IUPAC official way would be hex-2-ene, but Acer doesn't care between those two versions. And then this is still an alkene, double bond, that means alkene, and it is separated by a single bond, and so this is called a conjugated alkene. And then it's 1, 2, 3, 4 carbons, so it's a bute, and the double bonds are at 1 and at 3. So we said this is a 1,3-butadiene, diene, not a 1,3-butene, a 1,3-butadiene, because there's 2 double bonds, diene. And the IUPAC official way would be buta-1,3-diene, which would be a little bit better. But the bute is because 4 carbons. And then this is an alkyne because there's a triple bond. All of these are hydrocarbons. These are the famous hydrocarbons you put in your car, you burn them, which means to give oxygen, and it releases energy, and it allows your car to drive, and out the exhaust comes carbon dioxide and water. And that's the famous combustion reaction. You take hydrocarbon, you throw in oxygen, energy is released like crazy, releasing these bonds that have been there for hundreds of millions of years, from dinosaurs and plants and so on from that era. And that's released a lot of energy. Then we talked about this layer of molecules. So these are just hydrocarbons, only hydrogen and carbon, boom, oxygen-containing molecules. That's a whole other level of organic chemistry. Oxygen-containing molecules, of course, because the Earth changed to an oxidation, and we use this for life itself. So we have oxygen in here. Notice the carbonyl group, carbon double bonded to oxygen. These are the most famous oxygen-bearing molecules that come up on GAMSAT. You've got ketones and aldehydes, regular visitors to the exam. You see the only difference: hydrocarbon, 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 hydrogen. Just that is the difference. Ketones, if we have time at the end, we'll do a little naming. End in -one. Aldehydes end with al. Here are carboxylic acids. You see it changed to an OH. You should have in the back of your mind, what is an acid? As soon as you see that word, every single time, ask yourself, what is an acid? And if you have a chem degree, don't worry about any Lewis acids or bases. It's going to be the classic Bronsted definition. And if you have a non-science background, ignore what I just said. Just think of this: hydrogen donor. Actually, better to say proton donor. Proton is H+. So you have the ability to donate a proton, and that is what an acid is. And base is the opposite, proton acceptor. And that's the classic definition. So this is a carboxylic acid because it has this proton that it could donate. Change the proton to an alkyl group, and it's an ester. Carboxylic acids end in oic acid. So if we have time at the end, we're going to name some. And then esters, you change the carboxylic acid name. Then you end in O8 instead of oic acid, O8, O-A-T-E. And then you name this part, whatever this is, if it's ethyl group or propyl group or whatever it is. And whenever you have an alkane and you rip off a hydrogen and you attach this alkane somewhere, whatever name the alkane has, it's changed to alkyl. For example, propane becomes propyl, butane becomes butyl. Okay, so then that's the group that's here. Then we have acid halides. You don't have to memorize too much about this, but the X group in organic chemistry generally refers to a halide. And those are fluoride, chloride, bromide, iodide, 7th group of the periodic table. And then we just finished oxygen containing, boom, nitrogen containing, except for this one, amides and amines. So nitrogen is another important molecule, of course. These two molecules are the two most important molecules that you're breathing right now. Nitrogen, of course, 78% of air, 21% of air is oxygen. And these insert themselves into these hydrocarbons and create these incredibly important molecules. So we have an amide where we have nitrogen here replacing this group. And you might think of ammonia, amide, okay? Because ammonia is NH3. It's a household cleaning fluid. So you've heard of it, you've smelt it, and here you see it turning into an organic molecule. So the NH3 goes to NH2 as it attaches to carbon. This one, you don't have to memorize how to name it. And then we have this concept that recurs in organic chemistry: primary, secondary, tertiary, and quaternary. Okay, so this is a concept that keeps recurring. You'll see it over and over again. And it's referring to the central atom being bonded to a certain number of carbon-based strands or groups. So for example, we have primary, 1 hydrocarbon attached. We have secondary, 2 hydrocarbons attached. This must be a methyl group because it ends, but there's nothing there. So that must be a methyl group. So 2 hydrocarbons attached. Tertiary, 1, 2, 3 hydrocarbons attached. And quaternary, 4. And it's a quaternary ammonium salt. Somewhere in the back of your mind, you may have heard of ammonia, like we talked about. Okay, so if ammonia adds a hydrogen, okay, so that means ammonia is a weak base. And if you add a hydrogen to it, it becomes NH4. Then it's called ammonium. NH4 is called ammonia. Okay, so this is an ammonium salt. And then primary, secondary, tertiary again. Here's the central carbon, has 1 group. It doesn't matter that there's 2 carbons here. It only has 1 attachment to hydrocarbons. So primary. Here, secondary, 2 attachments to hydrocarbon. Tertiary, 1, 2, 3 attachments. I could have done the same thing with alcohols. Primary, secondary, tertiary, all attached to the central carbon. Okay, I think that's good enough. And just to remind you, for those, you have this differently in your handout, but I just put it down here, short form. So if it's the prefixes, of course, so 1 is meth, 2 is eth, 3 is prop, 4 is but. These are the ones that come up most often on the exam around here between prop and hept, but of course, anything could. But pent is 5, hex 6, hept oct, like an octopus, non for 9, sounds similar, dec for 10. Okay, and then you looked at this problem, and it starts with giving the rules for how to name bicyclic compounds. And you may wonder, why are we even looking at this? Who cares? I mean, and the reason is bicyclic compounds have been coming up on the real GAMSAT for over 20 years. Could you imagine? And if you look at the studies on this exam, you can Google it afterwards. You'll see that ACER, in a study of the exam, has admitted that that more than half of the questions recur. So more than half of the questions recur. So that means they were on last year's exam or the year before. So keeping that in mind, if there's a subject that keeps coming up, of course you want to learn, how to address it, efficiently. And that's why we're doing this. So even if you look at Des O'Neill's practice questions from 10 years ago, 10, 15 years ago, he has bicyclics. And bicyclics were last year and the year before. It doesn't mean that when you sat the exam, you saw it, because the person next to you might have different questions. Not all different, but will have some different questions. So that's why we're looking at this, because it's a recurring theme. Okay. And the reason, by the way, is because most students do not tend to do this in introductory level organic chemistry. So that means the non-science background student and the science student, usually, if they haven't done a good GAMSAT prep, usually are seeing it for the first time in the exam room. And so everyone has to adapt to this sort of learning. Okay. So it's called bicyclo because there's 2 cyclic components. Then there's numbers in brackets. The dec just refers to the number of carbons. So dec, we already said that's 10. Hex, we already said that's 6, and there's 6 carbons. Every corner of a geometric figure represents a carbon, and so they're enumerated there for you, and here as well. Oct for a total of 8 carbons. Now, the numbers in brackets. The numbers in brackets are telling you first of all, you identify which carbons are being shared between the 2 cyclic components. So that's the black dots. And the numbers in brackets are telling you how many carbons to get to the other one. So because there's 3 paths to get to the other carbon. To get from here to here, there are 3 ways to get here. You can get here this way, you can get here this way, and you can get here straight. So the rule is you take the biggest number first, then the second, which happens to be both same, and then the smallest number last. So you do it in that row. That's why it always has the biggest number first and smallest number last. At least that's the rule. So here, how many carbons to get to the other one? 1, 2, 3, 4. That's the 4. Next, 1, 2, 3, 4. That's the 4. Next, 0. There's no carbons in between these bridgehead carbons, and so it's 0. And over here, we go for the biggest root first. 1, 2, 3, 4, 5. Bang. Okay, 5. 1, 2, 3. Bang. And then 0. Done. So that deals with the numbers in brackets. Bicyclo, it's 2 cyclic components, and the dec is because of the number of carbons. And these are all saturated hydrocarbons. Saturated because each carbon is bonded to the maximum number of atoms any carbon can be bonded to anywhere in the known universe, which is 4. Carbon can never be bonded to more than 4 atoms. And so when it is bonded to 4 atoms, it's saturated. Yes, that's the same saturated that you're talking about with margarine and butter and stuff like that. It means that all of the carbons are singly bonded. And unsaturated margarine or butter or whatever, it's talking about having a double bond or a triple bond. Because by having a double bond or triple bond, that carbon is not bonded to the maximum number of atoms, which would be 4. Okay, so now let's get your opinions on the questions that you saw. I'm just gonna get this up here. Okay, so for question number 1, you were asked how many of the 5 following molecules are bridged? And what is your opinion? Please just post it while I draw. Just post your opinion while I draw, and then we will discuss it. Okay. There we go. So we have some C's and a D. Okay, so so the answer is indeed C. And the reason for that is that we are told that there are 2 different types. One is it's fused. Okay, so this is fused, and the other is a bridged ring, is where 2 rings have more than 2 common atoms. You see, it has one common atom between these 2 rings, and it also has this 3rd common atom. This one has 1, 2, 3, 4 common atoms between the 2 rings. So that's the difference. So when we look at these, only 2 common atoms, this and this, only 2, this and this. 1, 2, 3 common atoms. And over here, 1, 2, 3, 4 common atoms. So this one, this molecule and this molecule have are bridged. Now, it's time to graduate to the next level. Please write the names of each molecule. Okay, so write the name of each one of these molecules. And we'll just call this molecule 1, 2, 3, 4, and 5. As soon as you have a name, you can just type it into the chat window. You can say molecule 1 is blah, blah, blah. Molecule 2 is blah, blah, blah. You can just type it into the chat window if you're comfortable. So please try to name these 5 molecules. I'll give you a moment. Okay, so we have some lovely beginnings. For the first molecule, we have bicyclo. I think everyone can see that. So we have bicyclo 2,1,0 pentane. Bicyclo-2,1,0 pentane is indeed the first one. It's pent, 1, 2, 3, 4, 5 carbons. Bicyclo for these two components. 1, 2, back to start. 1, back to start, 0. 2, 1, 0 pentane, correct. So the second molecule, yep, we have some hexanes, 1, 2, 3, 4, 5, 6. So that's correct. Bicyclo, yes. And we have the 2, 2, 0. Yes, that's correct. So we have 1, 2, back, 1, 2, back, 0. So that's bicyclo 2,2,0 hexane, correct. Then number 3. Yes, I think we have somebody already who's got that. But perhaps not counted the carbons correctly. Yes, Harjo, if you can recount those carbons. Okay, so yes, we've got some heptanes coming in. Of course, I can't draw as well as you have it, but you will see that it's 1, 2, 3, 4, 5, 6 carbons, and then there's just the bridge over here. So 7 carbons, it's a heptane. And then you have 1, 2, boom, 1, 2, boom, 1, boom. Okay, 2, 2, 1 heptane. Bicyclo 2, 2, 1 heptane. That's number 3. And then for number 4, okay, I think I see Harjo, you hit the nail on the head. Leah, recount those carbons on number 4, please. Yeah, okay, you're seeing it. Okay, so it's there are 9 carbons. Okay, so it's 1, 2, 3, 4, 5, 6 carbons, 7, 8, 9. So it's a nonane. So it's a nonane. And then we count coming across. So the longest route, 1, 2, 3. Okay, then 1, 2. Okay, then 1, 2. Okay, so we have a bicyclo 3, 2, 2 nonane. And then last but not least, we have, it's going to be a deck, yes. And it's going to be a deck because there's 10 carbons. You can count them 6, 7, 8, 9, 10. And it's going to be bicyclo, 2 cyclic components. And then we have 4, 4, and then 0. Okay, great. Deaconess, don't worry, there's no autocorrect on the on GAMSAT. And that includes, by the way, for the section 2 typed essay, no autocorrect. So, okay, that looks pretty good. I think that looks pretty good, yes. Okay, so I have a question for you. What is the relationship? Because sometimes Acer will have a question to see if you get the point or if you have the overview of what's going on. And they can even ask you for an equation. So what would you say is the relationship between the numbers in brackets and the total number of carbons in the molecule? What is the relationship between the numbers in brackets and the total number of carbons in the molecule? I get your point. I'm sure you wouldn't get it right. I'm sure you wouldn't get it wrong, Pat. I'm sure you would get it right. But the numbers in brackets and the total number of carbons in the molecules, it'll be n plus 2. So it'll be whatever is the sum of what's in the brackets plus 2. Exactly, Leah. So, and of course, it's because the bridgehead carbons are not included in the numbers in the brackets. So you removed those carbons from the numbers in the bracket, and then that's what you get. But please remember, of course, we're just relaxed. We're having a good time. It's 2 months before the real exam, nothing to worry about. But Acer loves opposites. They love opposites. So they love, and in fact, they might even set the question up so it's the opposite of the opposite. So you just have to be very, very concerned. So you have what you know is true in your head. You just have to make sure you're making that ACER understands that. Okay, so let's move on to the next question. Name the following compound, and it looks something like this. So what is your answer? A, B, C, or D? Okay, so yeah, you guys are experts at this point. Okay, so we have bicyclo 2,2,1, hept 1-ene. So we have it's bicyclo, it's 1,2 to this one, 1,2 to this one, 1. So it's 2,2,1. We know that for sure. Hept, you count 7 carbons, and 1-ene because it starts, the double bond starts right there. Okay, so let's try something a little bit more. Let's just try something a little bit more. I'm gonna add, remember this molecule over here, I'm gonna add a double bond. Remember, I'm just gonna remind you guys from last week, is that one of the things we talked about, 3 fundamental aspects of organic chemistry for GAMSAT. 1, nomenclature. 2, geometric reasoning. And 3, pattern recognition. These are the most important things for organic chemistry. It's not memorization of nucleophiles and electrophiles. Nada, not at all. Mechanisms. How many mechanisms do you need to know? 0, 0, which is astounding for organic chemistry. Pattern recognition, geometric reasoning. So I'm going to show you this same molecule at a different angle. And of course, with my poor skills of drawing. Count those carbons and believe it. This is the same molecule, but at a different angle. Count those carbons and believe it. Or I hope you believe it. But I'm still adding something. I'm going to add this. Now, please name this. You're right, Zohal. You have to count from the bridgehead carbon that will give you the lowest number, because that's part of the rules. That's part of the rules for naming any alkene, any double bond, any triple bond. You have to use the smallest number. Okay, so we have an, yes, very tempting. So first of all, Harjo, I like the bicyclo. I like the 2,2,1, the 1,2, 1,2, and then the 1. I like bicyclo. I like 2,2,1. We have a problem with that oct. And yes, Valentina, this is the issue. This is the issue. How do we throw in the methyl group? That's the thing, is that the methyl group is not part of the bicyclo. It's an attachment. In organic chemistry, we call this a substituent or a ligand or substituent. It's an attachment. So the methyl group has to be named separately. Okay, so Maria has, she's on the right track. She said heptene, because this is 1, 2, 3, 4, 5, 6, 7. It's a hept, and it's a 2 because at the second carbon over here. So it's a heptene. Yes. So 1, 2, 3, 4, 5, 6, 7. Are you gonna? Yeah. Yeah. Exactly. Exactly. So it's a 7 methyl bicyclo 2,2,1 hept 2-ene. Now, did you think you would say that today? Perhaps you haven't said it yet, but you will say it later. Okay, is everybody okay with this? It's a 7-methyl, okay, because we number any carbons in the bridge last. And it's not that you have to memorize. You're not memorizing this. You go back to the rules that are provided to you, and that's the last carbon is the one in the bridge. So is everyone comfortable with this? We move on to the next unit. Okay, so just mean that the methyl is attached to the 7th carbon. Yes. And by the way, if there were 2 methyl groups attached here, it would be 7,7-dimethyl bicyclo 2,2,1 hept 2-ene 7,7-dimethyl. Yeah. Okay, so the actual name is of the original molecule is 7-methyl bicyclo 2,2,1 hept 2-ene. Okay, let's see. Okay. Okay, everybody's okay? Does it matter if you use comma or dot? That would never be a question on the exam, one or the other, but it's a dot, and Acer would give you the rules, but that's not what they're testing you on. So they give you the rules, literally. None of this do you need to memorize. You're just trying to get familiar with a question type that is a regular visitor. That's all you're doing right now. Okay. We are now going to look at the next unit. Okay, this is different question numbers, obviously, from what you have. I'm using question numbers from a different resource. One of the things we have is this 10 exam book with 10 practice tests with 5 in the book and 5 are online in the new 2021 digital format. And so I'm just taking a couple of questions from there. So the numbering is not your 3, 4, 5. Okay, so Huckles rule. You'll also find this in DES. You'll also find this has recurred over the last 20 years. And it's another classic sort of Acer GAMSAT conceptualization, and that is that they want you to be given some rules and then see something unusual and see if you can apply the rules on the fly. So that's basically what's going on. Okay, so so here we have Huckles rule, and you're given the 4 basic components of Huckles rule. And the molecule is cyclic. The molecule is planar. Planar means flat. And in this particular unit, it tells you that all the molecules are flat, so ignore that rule. Okay, and sometimes Acer doesn't even give you the rule. Sometimes they give it to you, sometimes they don't give you the rule because they don't want you to worry about that rule. Then the molecule is fully conjugated. Now, Acer wants you to worry about these last 2 rules. They like to emphasize these last 2 rules. One is that it's fully conjugated. We already talked about 1,3-butadiene. So now conjugation is more complicated than what it ends up being on GAMSAT. So I'm only going to talk about what GAMSAT is. And GAMSAT conjugation means a rotation of double, single, like that. Always a double bond and then a single bond, a double bond, then a single bond. So the classic, of course, is benzene ring, the benzene ring, which you saw in your, which you saw in the well, anyway, you can see the different components here. And the benzene ring is in your handout way at the end. Now, of course, this is the benzene ring. This is not the benzene ring. It's only when the benzene ring is an attachment, it's called a phenyl group. But this is actually the benzene ring. And you see it's double bond, single, double bond, single, double. It's fully conjugated is the expression used for this. And when a molecule is fully conjugated, it has increased stability. So the issue of conjugation comes up on the exam frequently. You're going to find a beautiful unit on conjugation in the pink booklet, which is called GAMSAT Practice Test by Acer. Okay, where am I? Okay. So, so we want to make sure that it's fully conjugated. So double, single, double, single. Okay. And then this is the rule that trips students up. The molecule has to have 4n plus 2 pi electrons, where n is equal to 0, 1, 2, 3, and so on. So this is the rule that makes students uncomfortable. And you're not just learning this with the hope that, oh, I hope conjugation's on my exam because I learned the expression for that. No, because this is a type of expression where n is an integer, which means a whole number, that comes up frequently in the sciences. So even if conjugation is not on your exam, there's going to be something else that is equation-based that requires you to be able to use the same principles we're about to apply. Now, I'm going to answer a question that some non-science students will be a little too shy to ask, but it's coming to their mind right now. And that is, what is N? You know, some students are wondering, what is it? Is it the electrons? Is it the double bonds? What is N? So this can be very frustrating for some students, but N is the solution to an equation. It is not something. It is not the electron. It's not the double bonds. And there's some science students who are going to confuse N with the principal quantum number N. And that is related to the atom's shells, which has nothing to do with these molecules. So N is just an integer and it doesn't mean anything. It's not referring to something specific other than it is the solution to an equation. Actually, it's not arbitrary. We will see in a moment how it's not arbitrary. It actually gives you some information about the number of pi electrons. So here I do need to explain a little bit about a pi electron, okay? So it is expected that you have just a little bit understanding that a single bond, S, of course, in English, sigma in Greek. The Greek letter S is sigma. So a single bond is a sigma bond. Now I'm just putting this in the back of your mind. There's a shell that's called S, and an S to S bond is sigma. An sp2, sp3, anything that has an S, when it's bonded, it's a sigma bond. There's shells, there's subshells called p subshells. I don't want to get you all confused, but for some of you, it's just revision. So I'm just going to say these words, ignore it if you have a non-science background. A P to P bond is a pi bond, because the English letter P and the Greek letter pi, it's the same. So P to P bond is a pi bond. This is the part that you should remember if you're a non-science student and a science student, is that it's the double bond. Okay, so it's the double bond. It's the second bond in the bond. Okay, so so you have carbon, double bonded to carbon. The first bond is going to be the sigma bond, and the second bond is the pi bond. And we are now going to focus on these pi electrons. Now, there's just one other thing that we have to do. So in other words, we're going to be counting these double bonds, okay? We're going to be counting these pi electrons in these double bonds. Okay, that's the key. So forget sp2, sp3, forget that for now. Just we're counting the double bonds. The other thing that you have to keep in mind is the number of electrons involved in a double bond. there are always two electrons involved in a bond. Anytime you see a straight line like this, it's composed of two electrons. Sometimes they're actually written as dots. You know, sometimes they're written as dots where one dot is representing obviously a single electron. And so we're writing a straight line to just do it faster. And so we have a single bond and we have a double bond. We're focusing on these pi electrons. So these are called electron pairs. You have to be very careful of the wording because Acer can trip you up in a dozen different ways. You know, did they ask me for the number of pi electrons or did they ask me for the number of pairs of pi electrons? Okay, and that's a concept that just comes up all over the place. I'm just going to look at one student's question. Can a molecule be only partially conjugated? Absolutely. So I drew this before and let's see. Okay, let me draw a little extra carbon. So I put a double bond here, a double bond there. This is a partially conjugated hydrocarbon. So, but this is not what we're being asked about. This has to be fully conjugated and it needs to be cyclic. You know, this has to be a cyclic molecule and fully conjugated. So every single carbon is going to be involved in a double bond. There has to be some double bond to every single, some pi electrons to every single carbon. That's part of the rules that we are given. Okay, so to simplify this, I know that sounds strange. To simplify this, let's see what this means. This N is 0, 1, 2, 3 stuff. Okay, so let's make N equal to 0. If N is 0, how many pi electrons do we have? N is 0, 4 times 0, that's 0, 2 pi. So we have 2 pi electrons. Let's try N is equal to 1. 4 times 1, 4 plus 2, 6 pi electrons. N is equal to 2. 2 times 4, 8 plus 2, 10 pi electrons. Okay, so let's hope that you see the pattern. They're adding 4. So this is 14, 18, 22, 26, blah, 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 blah. So it's all in 4, starting with the number 2. So that equation is simplifying these types of relationships, and it goes on forever. Okay, now let's keep all that in mind, and we will look at this. So okay, and yeah, Acer will love to make you uncomfortable by the size of molecules. and by the way, don't tell yourself, oh, they would never make me just count carbons in order to get a question right on the real exam. Yeah, sometimes on the real exam, you have to just count carbons or count hydrogens. And that's just part of the game. You just have to be very careful. Okay, so which of the two molecules obeys Huckel's rule? So we've already been told that this is the hexabenzochroinine molecule, and this is pyrimine. And so we have the two rules. We've been told that these are flat, so we ignore that. We should check to see that it's fully conjugated. And if you look carefully, every single one of these carbons has a double bond attached. Look at this carbon. There's the double bond. This carbon, double bond. This carbon, double bond. This carbon, double bond. This carbon, double bond. Every carbon has a double bond attached. These two molecules are fully conjugated. Now, I'm leaving the rest to you. So what is the answer for this question? So for you, this is question number 3. What's your answer? A, B, C, or D? Okay, so we have some A's. We have a little C, lots of A's there. Good. So We're going to start by counting up the number of pi electrons. And this is very easy. This is called geometric reasoning. I look at the pattern, and the pattern is not exactly a beehive, though that has been mentioned. But I look at the pattern and I can see that there are 3 double bonds, 1, 2, 3, 4, 5, 6, 7 times. So there's 3 double bonds, 7 times, 21 double bonds, which means there are 42 pi electrons, because every bond has 2 electrons. And then I look at my numbering and I can see that this goes up to 42. You can count it like that, or you can just say, as someone suggests, let n be, we have 4n plus 2 pi. So we have 4n plus 2 pi. And if you let n be 10, if n is equal to 10, that's 40 plus 2, that's 42. Hexabenzochroinene definitely obeys Huckel's rule, has the proper number. Okay, let's check this one out. Okay, we have 3 here, we have 1 here. That's 4 doubled, so that's 8. You can count them. 1, 2, 3, 4, 5, 6, 7, 8 double bonds. Double that for the number of electrons, 16. Look at our numbers. 14 obeys, 18 obeys, 16 does not obey. So the answer is, for number 3 for you, is going to be A. So that's correct. Can we make the whole equation equal to that number? And if n is a whole number, it follows it. That is correct, Zohal. You can take this equation and make it equal to whatever number of electrons that you end up with, like, for example, 16, solve the equation, and if n is other than an integer, then it does not obey, and if n is an integer, it obeys. Okay, so that's good thinking. Okay, next, as compared to pyrene, how many hydrogen atoms does hexabenzochroinene have? Okay, so A, B, C, or D. What did you guys get for that? So these are clearly hydrocarbons. Okay, so we have some C, some B. Okay, some C, some B. All right, so that looks quite good. So, so we can count the carbons. We have okay, so you see, these are all attached. So the fastest way to count the carbons, don't worry, you could take your time and you can count every carbon. You will finish. In the olden days, way back in 2019, when GAMSAT was 1.5 minutes per question, you wouldn't finish if you count these carbons. But you can count these carbons, okay, it's 42. But the fastest way to count these carbons is to see that these are shared here. They're always shared here. So all you have to do is say one of these has 6 carbons, 1, 2, 3, 4, 5, 6, and there are 1, 2, 3, 4, 5, 6, 7. So it's 7 times 6 is 42. So there's 42 carbons. And then, so 42 carbons. And then the next step is for the hydrogens. It's even easier if you use your geometric reasoning. So there's going to be, there are no hydrogens here, here, or here, because there's already 4 bonds. Carbon could be bonded maximum of 4 times. So for example, this carbon, 1, 2, 3, 4. So 4 bonds can't, 4 bonds, 4 bonds. So the only hydrogens are 1, 2, 3. That's it. 1, 2, 3. And then it has 4 bonds. So hydrogens are implied. And so there's 3 here. And how many times 3? 1, 2, 3, 4, 5, 6. So 3 times 6, and that gives us 18. And then we do the same kind of reasoning here. We have hydrogens here, like this, and everything else inside is already bonded 4 times. So then we have 3, that's 6, and that's 10. And then we count up our carbons for pyrene, and we have 16. Okay, so looking at our answer choices, as compared to pyrene, how many hydrogen atoms is this hexagon? So we're comparing 10 to 18. And so pyrene has more, but less than twice as many. And this is a kind of answer that, you know, professors don't usually have that in university, those kinds of answer choices, but Acer does. They have those kind of weird answer choices that they like to come up. And here is the coup de grace. Okay, the final question here. And yeah, I'm not sure how happy you guys will be with this one. But okay, so the final question, question 5, interesting. What is the best approximation of the simplest structure that can be repeated as needed to recreate hexabenzocornene? So the simplest structure, is it cyclohexane? Is it benzene? Is it both A and B? Is it neither? So what's the simplest structure to recreate this? A, B, C, or D? What is your answer? Okay, so we have lots of C's. I'm not sure, Mave, if you were referring to this one. Okay, so we have C's, A. Okay. So yeah, it's some of you will be having dreams about this hexabenzocornene molecule tonight. So the answer, okay, the answer is B, benzene. Now, I know when you look at this molecule, some of you have included cyclohexane in your understanding of this molecule, because you see the benzene ring. We saw that in nomenclature. You know, this is the very famous benzene ring. But you looked at this this part of the molecule, and you imagined this. So you saw this, and it looks like this. It genuinely looks like this. And this is, of course, the famous cyclohexane. Hex, because there's 6 carbons, it's cyclic, and it's an alkane. It's fully saturated, meaning that, as we said before about saturation, every carbon is bonded to 4 atoms, because although we don't draw it, these are hydrogens here. These are hydrogens, so that there's 4 bonds to every carbon. Okay, so this is the famous cyclohexane. This is the famous benzene, and there is no cyclohexane in this molecule. This is nowhere to be found in this molecule. It looks like it's there, but it's not there, because these are all singly bonded. This, yes, it's all benzene. It's all benzene. This carbon is double bonded. This carbon is double bonded. This carbon is double bonded. This carbon is double. There isn't, where's the single bonded carbon? It's not anywhere. And I know, you know, there's this, what? It's not fair, but look, do you see this carbon bonded to this carbon? It looks like on this side it's single, but you know that when this double bond is drawn here, it doesn't need to be here. This double bond could have been drawn here, and it's the same overall molecule. And this double bond didn't have to be drawn above this. It's the same meaning to draw this double bond here. And this double bond doesn't have, it's between these two carbons, this double bond. It doesn't have to be below or above as long as it's between. So this double bond could have been drawn there. They're all benzene. Yes, an optical illusion. So yes, this is, of course, this is delocalization of the double bond. Robert, this is the background of the information. Undergraduate studies, you would always be talking about resonance and delocalization. Acer doesn't care about that. They are into geometric reasoning. Can you reason based on the geometry? Now, don't get me wrong, there's resonance on GAMSAT, but the questions for resonance are based on geometry and pattern recognition. That's what it is. It's not based on some deeper knowledge of delocalization of pi electrons, which is what you need for a real undergraduate organic chemistry. Okay, well, guys, I guess, we'll probably do something like this again in a couple of weeks. I have to just check my schedule and see what's going on. I do want to show you, this new Master Series book. It's absolutely absurd. I'm going to make a video about it soon. And we're giving away the ebook versions every week. And these new ones, I'm going to say something in a video. I mentioned this before, but it's the first year out of 11 years that we're going to say this in a video. And that is that the practice questions in these new Master Series books are better than Desauneo. And that video will come out sometime this week, and I'll explain it, and I'll explain all the crazy new features of these things and the hundreds of pages that we've added. Okay, well, thanks for coming out. I am wishing you best of luck with your studies. And is it possible to get access to the answers to the HEAPS mock test because my access code expired? Yes, of course, you can still get access. The access is, it's something like, anyway, it's less than $20 to get access to if your access is gone, is terminated. And that's the HEAPS book, which is this other monster, which now has so many extra questions because GAMSAT is shorter than it was in 2019. So all that's changed. Okay, so wish you best of luck with your study. Those of you who are going to be attending the GAMSAT online tutorial on general chemistry next, I'll be with you in 3 minutes. And everyone else, thank you for showing up. We'll let you know about the next tutorial probably in a couple of weeks. And we'll definitely be spending some time on graph analysis in the month, within the next month for sure. Yeah, lots of funky graphs to evaluate. So good luck with your studies. Keep up your energy. You're nice and early. You just have to keep slamming at it. And good luck with your studies. See you next time. Bye for now.